is accelerating pre-IND by mapping disease mechanism to therapeutic candidates. And I want everyone to keep in mind that our entire framework is based off of two major things. The first one being disease diagnosis, the second being drug repurposing. So first I would like to start by talking about finances. So having a drug when it gets approved is usually actually the last step in a whole years-long process, sometimes accumulating to 4 or 5 years of pre-IND research looking into hit optimization, lead identification. And this process can take up to $5.6 million. Yesterday we heard from a lot of patient advocates talking about how their organizations first started off by bringing communities together. Slowly but surely, they started to bring in money, they started to raise money, and they started to put products into R&D trial. $5.6 million is a lot of money. And our entire goal for our project was basically trying to shorten that IND time by looking into mutations within genes. And those mutations can lead to something else. If something mutates in your gene, what happens? Our project was based off trying to find whether it's a loss of function, gain of function, whether it's a dominant, negative, and then finally giving a confidence score based off our predictions.
So our project goal is basically to configure the gene variant into the 3 categories you just mentioned: loss of function, gain of function, and dominant negative. We also want to provide the confidence scores on a scale of 1 to 10. In addition to that, we want to match the mechanism into the potential therapeutic strategies. So for example, if we know that a gene is the gain of function, we can use inhibitor to inhibit it. This process will accelerate the pre-IND, like you just mentioned. So our solution, we use an ensemble of models with insight from 4 databases. For example, one of the databases we used was the G2P, which is the gene to phenotype. It's essentially a database that detailed the gene disease association as well as information on the variants as well as mechanism. Parallel to that, to automate the process of manually analyzing literature to classify the mechanism, we automate this process by using large language model, and we scraped over 2,600 papers.
Okay, so just a little high-level overview of what's happening over here in this project. One of the central key data sets that we have in the project actually came from ClinGen, and this data set we fed to our ensemble. That is an LLM, specifically 5.4, along with 4 public databases. Now, what this ensemble ended up creating was mechanistic predictions as well as a confidence score. Now, this confidence score was calculated through the agreeability among all the models within the ensemble. Now, this is important for research within drug discovery, as well as research within gene mutations for rare diseases, specifically in the realms of process improvement.
We faced many challenges throughout this project. The first one was sort of learning the different database file types, sort of differentiating between what's accessible and what's non-accessible. Second, many of the databases that we tried or attempted to use did not provide the proper APIs or downloadable sources in order for us to extract the data from. And then third, after extracting the data, we realized that there was sort of like multiple aliases for the same disease. So then we sort of had to figure out how to parse through all that data and figure out how to sort it. And then fourth, of course, due to the time constraint, we sort of had to figure out how to balance between learning new software and also gathering a multitude of data sets in order to train our project. And then finally, many biotech companies did not publish detailed data on how specific variants disrupt protein structure to protect their intellectual property, which in turn sort of limits the availability of variant-specific mechanistic information for broader research and drug development efforts.
And now onto the actual product we produced. So our model, once again, as a reminder, takes in a disease and a gene, and it tries to establish how this gene is mechanistically involved in the disease. So our product is 400 gene disease pairs, and you can see on the top right, which is an excerpt from that, the mechanism and the confidence score. So for example, we can see in the top row, we can have BRCA1, which is a loss of function, and it has a very high score, so we're very confident that this is due to loss of function. And this result applies to about 400 genes that we extracted from the rest of the ClinGen/compute database. We were unable to compute for every one of the genes because of limited time. The large language model takes quite a long time to run, and we don't have all the compute. But this also leads us straight into what next steps could we take? So we have a framework here that maps diseases onto the data we want in the output. And we can consider two ways of expanding this framework. The first is, how can we add more pairs of genes and diseases? So easily, we can simply add all of the rest of the 90% of the data in the ClinGen database that we skipped for the demo. And in the future, we can add new pairs based off of new discoveries and literature. And the other is improving our ensemble. So for example, we can add new papers for our large language models to analyze, and we can also incorporate more databases into our process. In the future, we want to touch on predictive models, which will be able to take a mutation and predict its effect on the protein function, and therefore lead us into the mechanism. And now I'll pass it off to Edward to finish with a potential application that you could be using with our product.
Great. So is anyone in this room familiar with the term called drug repurposing? Yes, what is drug repurposing?
Using existing drugs for new cases. So if I have cancer or Prader Willis syndrome and something worse than that, maybe I could use that to treat something that also causes obesity in someone.
Exactly. And what is, in my opinion, so beautiful about drug repurposing is that it's not just about the science in itself. What makes drug repurposing work is the finances behind it. Drugs that already are approved for one indication, pharmaceutical companies sometimes do not pursue that third or fourth indication just because of financial reasons. That does not mean this drug doesn't work for other things. So right here is a really great case study from the data that we mined for have a predictive gene. Right here we have the cited 2 gain of function in CHD. So CHD is a rare mutation causing a gene to malmutate your heart, essentially. And in very severe cases of this disease, 48% of individuals do not survive beyond year 20. So in our study, what we found was that this gene is a gain of function. So theoretically, we could create or we could repurpose a drug to target upstream of the cited-2 gene in order to downregulate this gene. So what we found through the literature was A485. A485 is currently being tested for oncology. 40 to 50% of the solid tumor being treated with A485 is gone. Yet, this drug we found could have potential to work on an upstream gene called FOXO3, downregulating FOXO3 and theoretically perhaps causing an antagonist reaction with the cited-2 gene. Thank you so much for listening to our presentation, and we really, really appreciate it.